Yo, welcome back to another video. Today, we're going to be talking about something that, for me, is actually very, very difficult. And this is why I'm going to be talking about it, because it feels kind of simple, kind of easy, but then at the same time, it's also kind of difficult. So we're going to be talking about Hess's law. This is a very important law in chemistry. And what it states is that the total enthalpy change, it just states the total enthalpy change, that's pretty it. Now, what exactly is Hess's law? Hess's law is a state function, which means that in order to find the total amount of change in enthalpy, what you could do is you could just do products minus reactants, and you'll see what I mean. So essentially, let's say we had A plus B, and then this turns into somehow 2C. And then let's say the total enthalpy change was 200 kilojoules. Essentially, according to Hess's law, if we calculate the enthalpy for each individual element, and we did Hess's law, which in its formula is the moles of a compound minus the products, and this is the sum, minus the summation of the moles times the reactants. The reason why we go from products to reactants is because the products has the end over energy, and the reactants are reacting with energy in order to make the products, which is why we go from products to reactants. And so, how exactly does this law work? And we're going to go to an example. Let's say you had A plus B, and this turns into C plus, let's say, 2D. So then let's say that D had a total enthalpy change equal to 200 kilojoules. And then let's say that C had a total enthalpy change of 400 kilojoules. And then let's say B had enthalpy of 100 kilojoules. Then A was, 50 kilojoules. Essentially, you would write down Hess's law. So it'd be summation of the moles times the products minus summation of moles times reactants. And now essentially, since we have the total enthalpy change for each element, what we do is we just plug the numbers into our equation. So from here, we can work out with the C first. Since C is just 1 mole, we can say, actually, not C with the 1 mole. Let's just do products minus reactants. So we see here that the products are C plus 2D. So we can write down C plus 2D. You see why I put D in parentheses. Minus the reactants, which is moles times reactants. And then we can just put down A plus B. Now, the reason why I put D in parentheses is because it's being multiplied by 2. Since each mole is a coefficient in front of the element, we can see that D actually has 2 moles inside. So instead of being 200 kilojoules, and instead of C getting multiplied as well, we just write down 400 kilojoules for C plus 2 times 200 kilojoules minus the combined enthalpy change of A plus B, and it's 100 plus 50, which is 150. Now from here, what we can do is we can just find the total amount of kilojoules, or the total enthalpy change. So we can see here that 400 plus 2 times 200 is just 400 plus 400 kilojoules minus 150 kilojoules. So then in total, you get 800 minus 850 kilojoules, which is equal to 650 kilojoules. Now, this is the total enthalpy change. And since it's a positive number, we can say that the reaction is endothermic. What this essentially means is that we're putting more energy into the reactants. Not the reactants, the products, and we have less energy in the reactants. And so essentially think about it like this. Think about like boiling water. Since water has a high Ccal or not calorimeter constant, heat capacity, you have to put more and more energy in than something, let's say iron. If you were to both heat these up into, let's say like a change of 10 degrees Celsius, you'll see that it takes more energy for the water to do that instead of the iron. This would mean that water is somehow more endothermic somehow, something like that. But water is very, very endothermic if you put any heat to it. Exothermic is the opposite of endothermic. It just means that there's actually energy being released, since the reactants have more energy than the products. And we're going to see an example of this right now. So let's say we have the same equation, A plus B, and then C plus 2D. But let's change our things a little bit. Let's say the total enthalpy change of C is equal to 50 kilojoules. And then let's say D is equal to 100 kilojoules. Then let's say both B and A are 200 kilojoules. Essentially, we just write down Hess's law again. We just plug the numbers in. So now we get 50 plus 2 times 100, which is 250, minus 400, which would lead to, I forgot kilojoules. Just imagine kilojoules everywhere, which would lead to a total enthalpy change of negative 150 kilojoules. This will mean that the reaction is exothermic or is losing heat. Now, if you don't know how to tie an exothermic reaction, just think about an explosion. Just think about that. An explosion releases energy. And so you could think about it as a combustion, since it releases energy in order to make the boom. Essentially, this is what exothermic is. Imagine endothermic is just boiling water, while exothermic is an explosion. You're releasing heat while the water is entering heat. It's getting hotter, while the explosion is releasing energy. It doesn't want the energy, it's just boom, it just explodes. Just think about that. It's so good. Now, how else can we do Hess's law? Since Hess's law is a state function and it just says that we just have to do products minus reactants, and it's a summation, how about we add in order to find the total amount of enthalpy change? So let's say we had A plus B, which turns into C plus 2D. And then we're trying to find the total enthalpy change because we don't know it. So now, let's say that to turn B into C, the total enthalpy change for this would be 100 kilojoules. And then let's say to turn 2D into A, the total amount of enthalpy it would take, or the kilojoules, is equal to negative 150 kilojoules. You might be wondering, well, how can I find this if we're given these reactions? And you're so right. How can we do this? I'm baffled. I'm amazingly astonished, surprised. I'm just, I just don't know how to do this, but this is why I'm here. Essentially, what we can do is we can combine the multiple reactions because we can just sum it. That's how we can find it. Since it's a state function, anything that we do in the middle, it just turns out to be the same result as products minus reactants. So essentially, we just have to add these up like a little puzzle. So we see here that for the total reaction, we have A plus B, which turns into C plus 2D. For the first reaction, we see that we have B, which turns into C. Essentially, we know that B is going to be a reactant, and we know that C is going to be the product. So we can say that this reaction is good. However, we see that 2D, that turns into A. We see that A in the general reaction is a reactant, and we see that 2D is becoming a product. However, 2D becoming A isn't in the general equation though. So you're wondering, how can we do this? The answer is flip it. The answer is flip it. Flip it, flip it, flip it, flip it. This is because in order to take a reaction, if you have to do the same reaction but flipped, so let's say we were to turn A to the 2D, it would take the same energy. However, because we flipped this, we have to make delta H negative now. And essentially, since we made delta H negative, we have to multiply the negative 150 by negative. So now the total enthalpy change for A, which turns into 2D, is equal to 150 kilojoules. And now essentially, let me write down 2 and 1. Now essentially, what we can do here is we can just add the two reactions and see if they combine to make our general reaction. So for our products, we have A plus B, because those are the products. B is not products, reactant. A plus B is our reactants, and then it turns into C plus 2D. So now we get this general thing by flipping the second one. So this one's also good. So now we have our general formula, but how do we find the total enthalpy change? Essentially, we just sum. Since we know that we can sum the energies or the enthalpy, what we can do here is we can just do delta H1 plus negative delta H2. The reason why I do negative delta H2 and not just delta H2 is because delta H2 at the beginning was negative 150. However, during the process, we did flip it in order to become negative. So now we have delta H1, which is equal to 100, plus negative delta H2. Delta H2 in general is just negative 150. Negative turns into negative to positive. So now we have 100 plus 150, which means that the total enthalpy change for this reaction is equal to 250 kilojoules. That's essentially Hess's law in a nutshell. Obviously, you're going to be doing way more complex things in chemistry, in either in AP Chem or in college chemistry. However, this is a quick introduction to Hess's law, and you will be introduced to more state functions. However, this is how one of the state functions in terms of Hess's law works. It's just saying that no matter what process you go to, you get the same thing. Just get products minus reactants. And then from here, you can either do it this way. You either have problems like this where you have to, do the moles products to find the total enthalpy change for one reaction, or you're given multiple reactions and you have to solve it like a little puzzle, which is actually, this is actually the most fun for me. But essentially, this is Hess's law in a nutshell. It's just saying, what's the total enthalpy change, and it's just a state function. That's the whole summary of Hess's law. And so thank you for watching. If you enjoyed this, Like, share, subscribe, please. It helps a lot. I'm broke. I'm a broke college student. I need dining dollars. But essentially, this has been the video. Thank you for watching, and goodbye.